Okay, a little practice on how to solve Newton's second law problems. Now, how are you going to recognize a Newton's second law problem? You look if you have something that is going to relate force with acceleration. Newton's second law is what relates those two. So that's the key to identifying this is a Newton's second law problem. Now, I have here a very standard Newton's second law problem, a problem with somebody in an elevator. So we have an elevator, it has some rules here. It accelerates with an acceleration of 1 meter per second squared when you start moving. It's only for a short time, so I put here for 1 second, and then it travels at a constant velocity. Now, doesn't specify what the acceleration is when it's traveling, but it says constant velocity. Constant velocity means that acceleration, which is change in velocity divided by change in time, to match my words, I'll put the vector signs, is equal to 0 when constant velocity. Of course, that's because constant velocity means that the change in velocity is 0. So there's 0 acceleration when you're moving up and down. It's only when you start and stop that you have acceleration. You have a 100 kilogram man standing on a scale in the elevator. Now it says that scale measures his weight. What it really does is measures the force normal that the ground is applying to the man. And then we have a simple question to 2 significant digits. What does the scale read when the elevator is stationary? I'm pretty sure everyone can answer that already, but anytime you're solving a problem like this, you need to start with a free body diagram. Remember, if it comes up on a test, you're going to need to have your diagram. You're going to need to show your method and not just say, oh, the answer is this. So I start with drawing my elevator car. And in the elevator, I have my man, and he's standing on this scale. So now I'm going to look at this and say, okay, so what's my object? And I'm going to make my object the man. So then for my free body diagram, so this is a figure of what's going on for my free body diagram, and I sometimes will combine my free body diagram and just show the forces there. But for us today, I'm going to show a different free body diagram. Here's my man. Doesn't look the same. That's because I'm just drawing a caricature. In this case, my caricature has nothing to do with reality. Now I need to identify my forces that are acting on him. So forces are vectors, and I will show each force that's acting on the man. Now if I were to ask you in class what forces are acting on the man, you would say, well, there's a force of gravity. And by definition, the force of gravity is down. So I have my force of gravity. And we know that when we're on the surface of the earth, the force of gravity is always going to be the mass times g. Next, I'm going to have my force normal. The force normal is a force that is keeping him from going into the scale. So the scale is horizontal. To keep from going into the scale, the normal force is pointing out of the scale, which in this case is going to be vertical. So I have here the force normal. And that's all the forces that are acting on the man. Very simple. Now I am going to define my acceleration vector in the upward direction. So I'm going to draw a vertical vector and say this is my acceleration vector. I put the arrow over this. I didn't put arrows over the forces. We know they are vectors because I showed the direction. I will apparently make a mistake. I will go ahead and put a vector here and put the direction there because I have, remember, g is always a positive value, positive 9.8. I just put an arrow with down. That's probably not the best way to mark it. A better way is to indicate coordinate directions such as that. And now I can say, aha, that's in the vertical direction. This is pointing down, so it's in the minus y hat direction. Get rid of that. So there's my direction and my magnitude. Now for the force normal, because I don't have a value for it, I just put that there. Now I have everything clearly drawn in my free body diagram. Now I'm ready to get to work. So I identified that this is a Newton's second law problem. If it's a Newton's second law problem, I need to resolve each vector into its components. Well, these are already resolved into components because they're all in the same direction, the vertical direction. And then I apply Newton's second law. Now in this case, I'm going to apply Newton's second law in just one direction. So I will put Newton's second law, sum of the forces in the vertical direction is equal to mass times acceleration in the vertical direction. So that's Newton's second law of motion. So I look at my picture. The left-hand side I do independently from the right-hand side. I've seen some people who try to do the left-hand side and then say it's equal to itself. Well, that didn't help you. We need to find what the left-hand side is and equate that to the right-hand side so we can find something we don't know. So the left-hand side, sum of the forces in the y direction. Notice the force normal is in my positive y direction. So I'm going to write that as just Fn. I don't put the vector sign here because the magnitude of force normal is equal to, the force normal vector is equal to the magnitude of the force normal vector in the vertical direction. So here I just have the component, so it's just the magnitude of the force normal. Force of gravity is down, so that's going to be minus, and I'm going to go ahead and put mg because I know the force of gravity is mg. The right side is equal to may, and now I can make an equation for the force normal. Doesn't matter what ay is, it'll be correct for all ays. The force normal is equal to, move this across by adding it. I can factor out the m's, so that's equal to mass times g plus ay. Now I can answer the question that was given. For what I gave you, I said acceleration in the y direction is 0 because it says he's stationary. If he's stationary, his velocity is constant at 0, it's not changing. So in that case, the force normal would be just mg. So that would be his mass, 100 kilograms, multiplied by g. Always use 9.80 meters per second squared unless you're told otherwise. And so that's 980 newtons. Remember, a kilogram meter per second squared is a newton. Now I'm going to go a step further on this and do some other situations. This one was asking about him being in a stationary elevator. What if that elevator is moving? Well, this equation that we worked out is still going to be correct. So I will just take that and go to the next page and do it again for different situations. The next page will come up, trust me. There we go. So there's the equation I'm going to work with. Now I'm going to take another situation. So let's say starting up. If it's starting up, it said that it's going to have an acceleration in the y direction that's upward of 1.0 meters per second squared. So, using my equation, my force normal is equal to my mass, 100 kilograms, times g, 9.80 meters per second squared, plus 1.0 meters per second squared, the acceleration. And so that's going to be 100 times 10.8, or 1080 newtons. Now, I only have two significant digits, right? This only has 2 here. I add these together and it's 10.8. Ooh, now I have 3. And so my answer actually should be 1080 newtons because I have 3 significant digits when I add these together. That is, when I add 9.80 meters per second squared and 1.0 meters per second squared. My least significant digit in the first one is the 100ths. Least significant digit in the second one is the units. So in my answer, my least significant digit is going to be the greater of those two in the units. When I add this together, it's 10.8 meters per second squared. Now keep in mind, this actually illustrates a weakness of the significant digits because, if this had been 8.8, then I would have had only, 8.8 plus 1 is 9.8, and I would have had only 2 significant digits instead of 3. It doesn't make sense for that big a jump, but it's a rough way of keeping track of uncertainty. So that's what I would have just after it starts up. What about in the middle? Let's say you're going from the first floor to the 7th floor, and you're passing the 4th floor. What's the acceleration? According to the parameters given, you're going at a constant velocity after you get up to speed. So when traveling up at a constant velocity, the acceleration in the y direction is equal to change in velocity in the y direction divided by change in time, constant velocity, that's equal to 0. So if that's equal to 0, the acceleration, that's exactly the same as what I did with the first calculation where you're standing stationary. So I'm not going to repeat myself. I'll just say the force normal is equal to mg equals 980 newtons. What about when he's stopping? So when he's been going up, now he's stopping after ascending. Now in this case, he's been moving up, so his velocity is upward. But he's stopping, so the acceleration in the y direction, which is going to be Vy final minus Vy initial over delta t, the Vy final is 0 minus the Vy initial, which was upward, divided by delta t. Minus up means it's going to be in the downward direction. So acceleration in the y direction is equal to minus 1.0 meters per second squared. So the force normal acting on the person in the elevator in this case, mass times g plus ay, is equal to 100 kilograms times 9.80 meters per second squared minus 1.0 meters per second squared. So this is, now notice here, this is only 2 sig figs. This is 8.8 with only 2 significant digits. So I truly only have 2 significant digits in this answer. 8.8 times 100 is 880 newtons. We've covered every case for going up. Notice that when it starts going up, the man is receiving a larger force normal than he does when he's stationary. So we would say he weighs more when the elevator is starting up. When it's moving at constant speed upward, he weighs his normal amount. When it's going up and stopping, then he's going to weigh less than his normal amount. If he was coming down, and I will just put these out there without doing the calculation, if he's coming down, he's starting coming down, then we have a downward acceleration, and we're going to get the same force when he's starting coming down. When he's going downward at a constant velocity, the acceleration is 0, and when he's going down and stopping, that is going to be an upward acceleration, and he feels heavier. So that's the first type of force problem, Newton's second law problem, that we usually see in physics class. Now let's go on to some others. So the fuzzy dice in a car. While accelerating in Monica Purvis's 2014 Bugatti Veyron, which she wrote about in her lab, sorry Monica, you notice the fuzzy dice hanging from the mirror are angled back 30 degrees from vertical. What is your acceleration? Now I would ask you, how do you start? And your answer should be, well, first you need to read the problem carefully. I've done that. Then you need to draw a picture. So I will draw a picture. There's a nice Bugatti Veyron, by the way. So for my picture, I'm going to have There's the string holding my dice. There's my vertical axis. This angle is 30 degrees. I have my fuzzy dice out here. One die instead of having two dice. There's my fuzzy die. And now I'm ready to do some work. Now, notice, I did not give you what the mass of the die was. So some people might say, oh, we can't solve this. But of course, the wise person says, would he really give me a problem that I can't solve? Now that I've drawn a figure, I need to draw my free body diagram. For my free body diagram, I'm going to be a little more careful. I'm going to make my die. And then I'm going to show the force vectors acting on it. So just like before, I'm going to have a force of gravity acting on it. The force of gravity is going to be in the downward direction. Now some people might say, should that go above or below? The answer is, it doesn't matter. It matters that you show it acting on the object. So I'm going to put the force of gravity downward since that's what I did before. I don't know what made that one, but I guess I should back up and just make a new one. I must have double tapped or something crazy. So there is my force of gravity equals mg, and I'm not going to worry about showing a vector sign. The direction is shown here, and this is the magnitude of that vector. Then I'm going to have the force of tension acting on this. Now remember, tension is always acting in the direction in which the string leaves the object. So the tension is going to be going upward like this. So my force of tension is going to be something like this. And once again, that's at an angle of 30 degrees from vertical. So let's name this the force of tension. So I've drawn my free body diagram. The question was, what's the acceleration? So what's the acceleration? Well, first of all, what direction is the acceleration going to be pointing? This is a car driving, assumedly on a horizontal track, because if it's not horizontal, well, you know, it's going to be confusing. So the acceleration must be in the direction like this. We all know that it's going to fall backward if we're accelerating to the right. If we were accelerating to the left, it would have gone to the other side. So my acceleration must be a vector that points like this. What direction is that? Well, I'm going to make, once again, the same arbitrary xy definition, so that's in the x direction. Well, how do I solve this? Is this a Newton's second law problem? Of course it is. Otherwise, I wouldn't call this solving Newton's second law. How do I know it's a Newton's second law problem? Because I'm relating forces with acceleration. So, solving this, I know that Newton's second law says the sum of the force vectors is equal to the mass times the acceleration vector. Now, in the last problem, when I did the problem, I broke it down and I just did one direction, the vertical direction. I dropped out the vector signs. In this problem, I have this vector that is partially in the x direction, partially in the y. If I was going to do this with components, I would have to break that up into its x and y components. But this problem is going to be a lot easier to solve by using graphical addition than it is with components. So let's see how that works. How do we add vectors? We add them by tip-to-tail addition. So I'm going to use vectors just like I have here, the same colors. So first I put my force of gravity, and I know the length is changing. Then I'm going to put my force of tension, and so this is the force of tension vector, and the force of gravity vector. And I know that I have the equation here that says the force of gravity vector plus the force of tension vector is equal to mass times the acceleration vector. So that means that my resultant, going from start to finish, I should have made that a little longer, is going to be mass times the acceleration vector. Now recall, if you will, we know this angle is 30 degrees. We also know that the magnitude of this side here, actually I can just write like this, mg vector is the force of gravity. So we have the magnitude here, we have the magnitude here. Opposite side, adjacent side. I will just take the magnitudes, as I'll drop off the vector signs, and use my trigonometry to say that tangent of 30 degrees is equal to the opposite side, MA, divided by the adjacent side, mg. Now notice, I didn't give you the mass. A lot of people think, oh, we got a problem, we don't have the mass, we can't solve it because you can't calculate how big this force of gravity is. But when I did this calculation, voila, the masses cancel and I'm left with tangent of 30 degrees is equal to my acceleration divided by g. Now I'm looking for the acceleration, so acceleration is equal to g tangent of 30 degrees. Now how big is that? How big is that? I don't know. That's why we have calculators. So my acceleration is going to be g, which is 9.80 meters per second squared. Multiply that by tangent of 30 degrees. And that gives me 5.66. Now, do I have 3 significant digits? Going to go with, sure I do. Why not? So 5.66 meters per second squared. So I now have my answer. That's what the acceleration of this Bugatti Veyron must be if we are going to have the die hanging back at an angle of 30 degrees from the vertical. Now some may say, okay, you showed it graphically. What if I wanted to just brute force my way through this? What if I wanted to break it into components? Well, if I want to break into components, then what I'm going to have to do is take my force tension vector, which is green, take my force of tension vector, and then show my components. So I always take one line parallel to one of my component directions, one line parallel to the other, and make them so one starts at the beginning, one starts at the end, and they meet to form a right angle. So I have a right angle here. I have a known angle. This angle here I know is 30 degrees. I know the magnitude of this is force tension. I do not know what the actual number is. I just gave it a name of force tension. But now I can find my x and y components by using this triangle. Notice the x component. Can't see my x definition anymore, but there it is. My x component is going to be the opposite side. So I will have force of tension equals, and I'm going to put my x component and my y component as separate things. I actually like to write this out so I'm mathematically correct. So I will have ft sine of 30 degrees in the x direction. It's positive because it has to go from here to here. If I'm going to start here and end up here and I add vectors, it's going to have to go to the right. Then it's going to have to go up. So up is positive y direction, so I'm going to have plus ft, this is the adjacent side, so cosine of 30 degrees in the y direction. Now, I had one other force. The force of gravity is equal to, how much is it in the x direction? None. It was vertical. So 0 in the x direction. In the vertical direction, the force of gravity was down, so that's minus mg. Now notice I'm not putting the vector sign here for g, I'm putting the magnitude in the y direction. Now I take these, and I can apply Newton's second law in each component direction. So in this component direction, I'm going to have ft sine of 30 degrees plus 0 equals max. Didn't quite fit, but I'm going to move that. Now it fits. And I should have actually put here, that was sum of the forces in the x direction equals mass times acceleration in the x direction. Over here, sum of the forces in the y direction equals mass times acceleration in the y direction. Sum of the forces in the y direction is going to be ft cosine of 30 degrees minus mg equals, now what's the acceleration in the y direction? Since the car is accelerating in the x direction, acceleration in the y direction is 0. Acceleration in the x direction is what I'm looking for. So now I have two equations with two unknowns. What are the unknowns? One of the unknowns is the acceleration in the x direction. Actually, let me change the color on that. One of the unknowns is the acceleration in the x direction. The other unknown is the force of tension. So since this one has acceleration in the x direction, I would take this equation and solve it for the force of tension. That is, force of tension is equal to mg over cosine of 30 degrees. Then I put that force of tension in for this force of tension, and so that's going to give me an equation that I don't want to start a new page just to finish, so I'm going to write up here. That would give me, but that color doesn't work there. Doesn't work because you're going to get confused with the other work. So in blue here, that's going to give me mg over cosine of 30 degrees. So there's my force of tension substitution. Then times sine of 30 degrees is equal to max. Divide both sides by m, and you end up with ax is equal to g. Remember, sine over cosine's tangent. Tangent of 30 degrees, which is the same equation that I had before. So that's the brute force way. This way here, the way done in green, finishing up in blue, will always work. The way I did with the graphical, well, technically it'll always work, but many times it will be difficult. All right, let's look at another problem. This is the last problem here. And this is what we call an inclined plane problem. So I have a block that's on this incline, has an angle of 33 degrees above the horizon. So let me draw that in right off the bat. This angle here is theta equals 33 degrees. And the block has a mass, m equals 60 kilograms. And then it says, what is the acceleration of the block if there's no friction? Well, what we have to do is make a free body diagram. Okay, that was poorly chosen. I actually need to back up a number of places here to get rid of all of that, because I don't want that angle written where I wrote it. That was a mistake on my part. Let's just go like this. Work on layer 2 so I can't delete. Right, this won't erase anything anymore. So theta is equal to 33 degrees, and this is my angle theta right here. Here's my mass. Now I need to put the forces that are acting on the mass. Now the first and most important thing that people forget is the directions of the forces. The force of gravity is always going downward. So there's the force of gravity. The force of gravity is equal to mg, just as it always is. Now I also have the force normal, but remember the force normal is a force normal to the surface. It doesn't mean upward when it's force normal. I have to look what direction is normal to the surface, the direction pointing out. So the force normal vector is going to be a vector that points, I wanted to do a straight line there. The force normal vector is going to be a vector that points like this, pointing straight out of the surface. That's my best attempt at pointing straight out of the surface. So that's my force normal. And now I have to figure out what the acceleration is. So, well, we've already done something here that would make this a little easy. We can do this with a triangle in a fairly simple fashion, just like we did with the tassel. So I will draw my figure bigger with just the forces. I have my force of gravity. Well, actually, let's write Newton's second law first. Sum of the force vectors is equal to the mass times the acceleration vector. So now I need to draw this out. So my force vectors, I have my force of gravity that goes straight down. Now, does it matter which one I put first? No, it does not. Then I have my force normal, which is going to be going up like this. And finally, I'm going to have, I'm going to have my acceleration. Now, you got to think about this. What direction is it going to accelerate? It's going to accelerate down the slope. So that's my acceleration vector. So if that's my acceleration vector, then when I draw that here, I'm going to have a vector that goes like, And so I can label these. This side here is MA. This side here is force of gravity equals mg. And this side here is force normal. Once again, I have an angle. This angle is 33. The trickiest part for this is which angle in this triangle is that 33 degrees? And the answer is, well, the simple answer is it's this one. This here is my angle theta, the same as that. Now, how do I get that? Notice here that theta is the angle between horizontal and the incline. Here I marked theta as the angle between vertical and the normal. Now in two dimensions, normal, actually, once again, change color. Normal is perpendicular to the incline, whereas horizontal is perpendicular to vertical. So this is the angle between those two, horizontal and incline. This is the angle between the perpendicular to horizontal and the perpendicular to incline. So that's how I know this is the angle that's the same as my angle of incline. Note that the acceleration is perpendicular to normal, so I do have a right triangle with the right angle right here. So with that as a right angle, this angle known, I look at the sides I have information about. Notice force of gravity, which side of the triangle is that? It's the hypotenuse. The mass times acceleration is the opposite side. So using my trigonometry, I'm going to have the relationship that opposite over hypotenuse is sine of theta is equal to my opposite side, which was MA, divided by my adjacent side, MG. Lo and behold, the masses once again cancel. I gave you the mass, but it didn't matter. And I have sine theta is equal to A over G. So once again, solving for A, the acceleration is equal to G sine of theta, which is going to be 9.80 meters per second squared times the sine of 33 degrees, Well, of course I don't know that. I know sine of 33 is slightly bigger than a half, but I don't know how much bigger. So I do 9.80 times sine of 33 degrees, and it tells me that that is 5.34. Now this is an important outcome. What is making the box slide down the slope? It's the force of gravity. The force of gravity is down. It's not pointing down the slope, but the force of gravity has a component that is pointing down the slope. And it's that component that's pointing down the slope that's making it accelerate. Now, the steeper I make it, the closer gravity is to down the slope. That means a bigger portion of the gravitational force is going down the slope, and it's going to accelerate faster until I get to a vertical where sine of 9 degrees is 1, and it would have an acceleration of 9.8 meters per second squared. And of course, if the angle was 0, if it's flat, sine of 0 is 0, and it'd have 0 acceleration. Now, just like with the last one, let's see how this would work if I brute forced it, if I broke things into components. This is where things get a little interesting. You look at my vectors, I have this vector and this vector that are perpendicular. If I use a component direction that has horizontal and vertical as my x and y, I'm going to have to break both of these into components. This one here will already be resolved. It'll be easier for me if I rotate my axes and set it so I have my y-axis in the normal direction, and I have my x-axis in the direction up the slope. So this here should be a 9-degree angle. If I do that, then this vector is already resolved. Actually, yeah, there's only two forces. This is acceleration. This vector is already resolved, and that's the only one that has to be broken into components. So I'm going to do that. So drawing a bigger picture here for the vertical, that is the force of gravity. So here's my force of gravity vector. And then I want my component directions. So I have one, boy, I hope I did that right. That doesn't look very good, does it? Well, it's going to have to do. And the other one starts here and goes like, yeah. So now I have my right angle here. Which angle is theta? Theta is once again going to be between the perpendicular to the normal and the perpendicular to horizontal. So this angle here is theta. This side here was force gravity equals mg. So to find the, actually I want to do that in red. So this side here is opposite. Remember, I made this so my x-axis goes to the right and the y-axis goes up. You might wonder, why do I have the x-axis going up and to the right here when my vector is pointing down and to the left? The reason is we always want a right-hand coordinate system, which means you have x before y with that 9-degree angle going in a counterclockwise direction. So my x component to start here and get to here means that I'm going to have to go opposite to the y direction and then opposite to the x direction. So they're going to be minus, negative for both directions. Making my vectors, the force of gravity vector in the x and y directions. In the x direction, that's opposite side, so it's going to be minus, because of the direction there, mg sine of theta in the x direction. The y direction, it's again minus, mg cosine theta. My force normal vector was all in the positive y direction, so 0 in the x direction, and positive force normal in the y direction. Got those done. Once again, I'm at the bottom of the page. I am just going to take this and move it to the next page so I have plenty of room to finish this out, and that's good enough for me. And we wait, but don't worry, here we go. On to the next page where I paste this. So now I'm going to use on this side my pen. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. Now remember, the x direction is going like this. The y direction is going like that. So the acceleration in the x direction, I don't know what that is. I'm trying to find that. Adding up what I have on the side, I have minus mg sine theta equals max. Well, I'm looking for the acceleration in the x direction. I know everything else here except for mass, but the mass is going to cancel. I just divide both sides by m. I have a sub x is equal to g sine of theta. So what good is this equation over here? Well, it allows me to find the force normal. How big is the force normal? Sometimes people think, oh, the force normal is equal to the weight. Well, we already saw with the elevator problem that the force normal is not always equal to the weight. In this case here, I would just say sum of the forces in the y direction is equal to may. Now, it can only move in the x direction if it's going to stay on that plane, so the vertical velocity, or the y direction velocity, is not vertical, is going to be 0 and constant, hence the change in velocity is 0 and the acceleration in the y direction is 0. An arrow to 0 just means that term is 0. So plugging in what I have in my column here, I always like to put positives first if I can. Force normal minus mg cosine theta equals 0, which means that the force normal is equal to mg cosine theta. So now I was able to calculate both the force normal and the acceleration just by the brute force method. Now you can see breaking into components here was not very difficult, but it was more difficult than doing it graphically. So this is some examples of how to solve Newton's second law problems. Hopefully this helps you as you go through the class doing your homework and learning and preparing for the test. Alright, have a good evening.